All right, everybody, we're going to talk about the impulse momentum equation. We're going to talk a little bit about what these terms are, what they represent, and how we're going to use them in class. So let's kind of start off with this. Momentum is kind of one of those physics words that's a little bit tough to describe. So here are kind of my attempts to kind of get you going down that line of thinking. But momentum, think of it as the amount of oomph that something has. And what I mean by that is, how much would it hurt if this thing like hits you? If we know if we're getting like punched, right, or something, or a ball hits you, well, there's a couple of things that dictate like how much effort it goes into putting a stop to that, or how much is it going to hurt when it makes impact with you. I mean, maybe you can think about those things, right? Obviously, the mass of the ball is going to have an impact on that. Obviously, how fast it's traveling, the velocity of the object. But one kind of third component too is the amount of time that it's in impact with you. So momentum and impulses are always going to be about collisions. And while we are going to have things sort of colliding a lot, a collision is sort of a more generic term for sort of when things come in contact with one another, we're going to kind of see what happens. So there are two versions of the impulse equation, which is good and bad, right? Because there's sort of two approaches. But both of these equations will help you maybe have a better understanding of what goes into solving for the momentum and sort of what momentum is. All right. So here's our first equation, which is the momentum. It's going to be a vector measurement. We have these arrows. So we spend a lot of time and energy in being scalar. We're now back to vector measurements, which means when we report an answer, we need both a magnitude and we need to go back to that direction. Notice that the unit, or how we abbreviate momentum, is a lowercase p, right? And that doesn't really make a whole lot of sense. We've already used the lowercase m for mass, and so I guess we're just using other variables. It is what it is. But you'll notice here that the momentum an object has, or an object's momentum, is related to the amount of mass that it has and the amount of velocity that the object has. So it's kind of related to the kinetic energy, which we've seen is these variables in a slightly different abbreviation. Okay. Now, if we kind of take a look at what the units for momentum will be, we're going to have something slightly different. We don't have sort of a person to name it after, like a Newton or a watt or something like that. So we have mass, which is measured in kilograms, and we're going to multiply that by a velocity, which is in meters per second. So that's going to be the units. It's a kilogram times a meter per second. Okay. Now that sounds really similar, but is not the same for how we sort of abbreviate what is a Newton, which is a kilogram times a meter per second squared. Remember, this is kind of related to Newton's second law, which is the net force and the mass of a system times its acceleration. So again, going back to the equation, right, that's going to help us come up with what the best unit is. Again, there's no abbreviation. It is a kilogram times a meter per second. So if I were to ask you, which of these objects has the greatest momentum? A large truck that's going 30 meters per second, a small car that's going 30 meters per second, or the Empire State Building, right? So sort of tricky, but not tricky. We need to have both a mass and a velocity in order for an object to have momentum. Even though we have a really big object, such as the Empire State Building, if an object does not have any velocity, then it does not have any momentum, right? Yes, it would be hard to move, and yes, it weighs a lot and all that good stuff here, but momentum is requirement or relationship between an object's mass and how fast it is moving. And so in this case, the large truck, we'll assume is going to be a heavier mass than the small car. If they're both traveling at 30 meters per second, which one would hurt worse if you got hit by them? Which one would take more effort and sort of time to come to a stop, right? Is a way to think about what momentum is. Let's take a look at how that other kind of equations that go with this. And so the first, Newton's first law as it relates to momentum, the first law states that the velocity of an object will not change unless an external force acts on it, right? So for every force, there's an equal and opposite force that acts on it, things like that. So that's kind of what we've got in this equation. If there is a net force that changes the velocity of an object, right, it's going to also change its momentum. So anytime we're changing an object's velocity, we're going to have a change in momentum. We'll talk about that in just a second. Okay. So as it relates here to the second law, right, that's what the first law kind of equation variant is this. We're going to take a look at the second equation and how it relates to Newton's second law. So let's suppose there's an event that causes the momentum of an object to change. We're going to talk about that event as an impulse. An impulse is something, or we use that term to describe when the momentum of an object is changed. So going back to our equation a second ago, what are sort of the ways in which momentum can be changed? Well, we only have two. An object's momentum will change if there's a change in mass or a change in velocity. For this class, right, and the equations and things that we're going to be doing, Usually that's going to be a change in the object's velocity. Very rarely do we have sort of a collision where part of it like breaks off and the mass disappears or changes. That's just not something that we do with. So usually an object is going to change its momentum because it has a change in its velocity. And we can kind of see that, right? We talked about this simple kind of variation delta. The change in momentum is equal to an object's final momentum minus its initial. So, right, delta is always the final minus the initial. And so let's consider what we see for Newton's second law. Newton's law says that the sums of the forces acting on an object is equal to its mass times acceleration. We're going to use this Newton's second law to kind of relate how net forces or the forces can relate to a change in an object's momentum. So let's kind of substitute a little bit here. We know that the acceleration of an object can be sort of described or written as the change in velocity over the change in time. And so we're going to take this variant and kind of plug it back into Newton's second law. And we see we have this sort of blue substitution. Now, we don't normally talk about expanding equations, but just for the sake of, imagine what it would look like if we sent mass through this kind of top part, the numerator. So we have mass times final velocity minus mass times initial velocity over delta t, right? This is all relating these two things. Now, why would we sort of expand that fraction? Well, we just talked about what m times v would be. And so this is an equation for momentum. So we can write that in here. Then object's final momentum minus initial momentum, right, over the delta t is equal to the net force. Now, how does that relate? So we're going to rearrange this a little bit. We're going to kind of clear off that delta t and kind of isolate and get momentum by itself. Notice, though, we have delta p. So a little bit of a variant here. The change in momentum can be mass times the change in velocity, or the momentum, the sort of what it has at a particular instant is its mass times its instantaneous velocity. In this equation, though, you'll see that the change in momentum, this is going to be referred to as an impulse, can be solved if we know the net force acting on an object and how much time it is. So go back to the video at the beginning of this video when I talked about what is momentum. Yes, it's related to an object's mass, and yes, it's related to its speed, but also talked about like how hard would it hurt if you got hit by this object. That's dependent upon, right, like a punch, right? The magnitude of the force of the punch as it hits you, and also the amount of time that it sort of spins against your body. Both of those things are going to dictate sort of how hard the impact will be. And so there's a lot of things that go into this. But again, two equations, m times delta v is momentum, or the net force acting on an object multiplied by the total time that the object is in contact, right? So memorize those two equations. We're going to see that as the momentum, impulse momentum equation. We're going to kind of be able to set both sides equal to one another as we move forward in our lessons. Okay. So let's go back to kind of our the equation that we just derived, right? An impulse, that's an object's change in momentum. So delta P is kind of hidden in this word, is equal to the net force times the change in time. Is it possible for an impulse to be negative? And if so, what would be true, or how would that happen, right? Remember that impulses and momentums are vector measurements. So it is possible to have a sort of negative vector acting on that. So what would be required, right, is that we would have to have a negative force kind of acting on the object. So we have an object that's moving in one direction, sort of a positive velocity. If we had an impact, a force that was in the opposite direction, right, what would happen to this object? It would slow down. So it's kind of related to kinetic energy, right? But an impact that would be negative would slow an object down. Whereas if we have an object that's moving and we sort of had a rocket engine that blew or did something happen where we can accelerate it and make it move faster, that would be sort of a positive impulse. So again, related to work and kind of energy, positive impulses mean that the object is going to be sort of accelerating and moving faster. Negative impulses is sort of in the opposite direction, and the object should be slowing down. Now, what does this say? The impulse, right, is related to the net force acting on an object and the amount of time. So consider for several impulses, let's just say that we are trying to stop a big car and it's moving in one direction, right, versus a small car, something like that. For given impulses, if this left side is remaining constant, what's the relationship between these two variables, right? So if this is some number, how does f and delta t relate to one another such this left side can be constant and always the same? So again, kind of using our algebraic relationships here, right? If this is always kind of 1, and if the force were to increase, well, then what would have to happen to the amount of time to sort of get the same number? Or if the net force would decrease, what would have to happen to this delta t such that we could get the same number over here? And hopefully you can see that now, or kind of process this, that force and time have an inverse relationship. So let's consider what that means in terms of how airbags work when they deploy during a crash. How could we use the impulse momentum relationship, that's this equation here, to explain the effectiveness of airbags in the car? So we kind of have this relationship here, this kind of graph that's showing that force is a function of time, right? Well, during an impact, right, your body is moving at a particular velocity. And what's the purpose of the airbag is they deploy and they sort of stop you. Now, a lot of people tend to think about, right, it provides that cushion, and it does. But more importantly, right, it slows the impact down, right? So think about what would happen if you weren't in a car that had airbags. So the airbags didn't play, right? You're moving, right? You crash, but law of conservation of energy, mass, right? Newton's law. Once an object's in motion, it's going to continue to be in motion, right? So eventually your head's going to collide with sort of the dash or the windshield. That's tragic and horrible, and why you should, wear your seatbelt. But the airbags deploying, well, that's process. You're still going to be traveling the same speed. You're still going to be colliding. You're still going to be slowing down. But that airbag provides sort of this cushion, which slows down the amount of time before you sort of make impact. So what's happening when airbags deploy is that this delta T is going to increase. It's increasing the amount of time before your body comes to a stop, right? Another way of saying it's to slow down the amount of time before your sort of velocity becomes zero. So what's the relationship? Now, regardless if you wear, seatbelt or airbags or not, the impulse delivered to you, if you're traveling in a 50 miles an hour and you become zero, that left-hand side is going to always be the same, right? So what do we talk about the relationship between F and delta T? As the temperature, as the time increases, what do you notice is happening to the Y value here, right? It's going to be an inverse relationship. So by slowing your body down, right, there's less force exerted to your body over a longer period of time. And because it's less force slowing you down, there's less of a chance of you having a traumatic injury, right? Versus, again, what if you sort of didn't have an airbag, or you didn't have your seatbelt, and you just slammed the front of the car? Well, that delta T between your going 50 miles an hour to zero is incredibly small. And as that amount of time decreases, the amount of force delivered to your body is significantly higher. And that's going to have a very traumatic effect on your body. So wear your seatbelt. All right. So let's give another example. Let's consider a batter, right, that is trying to hit a ball and knock it out of the park, hit a home run in baseball or softball, something like that. Well, the amount of energy required to get the ball from home plate over the field is always going to be the same, right? The batter needs to hit the ball hard. But what are some things that a batter can do to sort of help their chances or help kind of get the ball out of the park? So obviously, when batters hit the ball, they want to have the greatest impulse possible, right? So what's some options? What are some ways that they can increase their impulse by considering the left-hand side? Obviously, one thing that they can do is to swing with a greater force, right? Power hitters, right, have the greatest sort of swing. But alongside of that is you could swing with the same force, but you could just sort of get the ball or get the bat around your waist in a shorter period of time, right? And so those two things are related. Not only do you have to sort of swing, harder, but you got to swing fast, right? The getting the ball around or the bat around to the sort of front side will kind of help the exit velocity of it. Additionally, kind of related to our first equation, right? Well, remember that the net force and the time are related to the impulse, right? Which is the change in momentum, which is mass times velocity. Well, what could sort of give the ball a greater exit velocity is to hit the ball with a greater sort of mass behind it, right? The impulse that the bat delivers to the ball are going to be equal. We'll talk about that conservation of momentum in a little while. But you may not know this, but batters, when they sort of choose their bats, they have different weights to them. So again, related to how fast can they swing the bat is related to the weight of the bat. And so those are all ways that, batters can sort of help accelerate or to help their chances of getting the ball out of the park. Let's go to kind of some graphs and number problems here. This is the picture of the Saturn V rocket, sort of an older generation that first delivered the astronauts to the moon. One thing that's impressive about this is that this thing weighed 3 million kilograms. And so you can imagine to get 3 million kilograms off the ground required a huge amount of energy. And that's what we see here. There was a 3-stage rocket. So this is sort of phase one. It broke off, and then phase two ignited. It broke off, and then phase three. And then way up here is where the astronauts actually were housed and what they were kind of staying in as they orbited and got to the moon. So we're going to kind of consider what the plot of this sort of three-stage rocket would look like. You'll notice that 34 million newtons of thrust was delivered during the first stage. All right, 4,400,000, and then 1 million newtons as we go. You can kind of see these seconds was the burn time, right, for the amount of time that the rocket was acting on it. All right. So we're just kind of looking at the first stage here, first two, and you'll notice that this y-axis has changed a little bit. Those two numbers are the same as we see kind of here. This 34 million. Yes. Yes, million brain fart there. Is related. This is 1 times 10 to the 6, right? So that 34 is sort of peaking here. All right. So what would we kind of learn from the area under this curve, right? We had a force as a function of time. We haven't seen something like this before. We've had sort of velocity and positions as function of time. This is a new variable. So think about the relationship here. The area under the curve, we're going to multiply force. We're going to multiply it by the change in time. Where have we seen that kind of equation for? So indeed, the area under a force as a function of time is the momentum and the impulse. That's the equation, the sort of Newton's second law version that we derived earlier. Net force times the change in time represents the impulse. Again, impulse is just a name for the change in an object's momentum. So we could use this graph to determine what the final velocity of the rocket would be after stage one, right? So going back to the kind of picture here, right? So, right, we're at initial velocity is 0. So what would be the final velocity of this whole system after this complete burn happened, right? And we're going to abbreviate a little bit. There's a little bit of time where, right, it wasn't at full thrusting power, but we're going to kind of approximate what the velocity be. So how can we figure that out? So this is kind of, again, the blend of the two equations. I want to point out here too, in some of the textbooks, you'll see this capital J, just to screw with you. It's just another letter instead of the lowercase p as a way to abbreviate momentum. I'm not going to talk about it too much because we don't use it in this class, but future textbooks and things may have that. But for all intents and purposes, this is going to be lowercase p. And remember, there are two equations to solve for that. An object's net force times the change in time, or momentum can be solved by an object's mass times the change in velocity. So if we apply this sort of these 34 million, newtons of force, right? That's the y-axis here, to the 3 million kilogram rocket for that 165 seconds at burn time, what will be the change in the rocket's velocity? So here's that impulse momentum equation. We have these two things are equal. They're synonymous with one another. These two words or these phrases mean the same thing, right? The I, representing the impulse, is equal to the change in momentum. Again, these words are the same. If the words are the same, they represent the same thing, we can set them equal to one another. So again, we have the two equations, the net force acting on the rocket for the amount of time that the rocket is pushing is equal to the other version of momentum, which is an object's mass changes times its change in velocity. So we've got everything on the left-hand side provided by this area curve. We're interested in determining what the final velocity will be. We're going to kind of use the numbers from the equation and the reference sheets. And so, again, think about that. That huge rocket that is accelerating out of Earth's atmosphere is traveling at 1,900 meters per second. So, again, just crazy to think something that big could be traveling at that fast, right? Now, here's a thought for you. NASA reported that the final velocity of the rocket was actually higher than what that velocity would be. You kind of see NASA said, hey, after stage one, the rocket should be traveling at 2,756 meters per second. So why is that, right? Well, physics can't lie. Why is it that the actual exit velocity or sort of velocity after that rocket would be higher than? So again, go back and think about what's happening to the rocket as this thing burns, right? Well, part of this total mass is 3 million is the amount of fuel, right, that's in this rocket. So as the fuel decreases, that's less mass. And we know that less mass is easier to accelerate. It has a final velocity, right? So as the mass of this is sort of decreasing, right, the object can be traveling faster. So hence why the discrepancy. But again, we talked about working around a little bit anyways. All right, let's use kind of a similar kind of approach. Let's determine the change in momentum for this object, a total change in momentum for the graph display. And so again, we kind of have this three-section graph, right? We have force times time. So again, different than the rocket problem separated out. This is just a graph of the force acting on an object over a certain period of time, right? So we can see kind of the triangle here. We have a rectangle here and another triangle. Notice that this is all sort of in the positive domain. It's above the zero. So even though this value is going down, that doesn't mean that the object is moving in the negative direction, right? It just means that the magnitude of the force acting on it is decreasing, but all of these are positive forces. So all of these would be sort of pushing the object in the same direction and causing it to accelerate. If we wanted to solve for the change in momentum, remember that is synonymous with impulse, we could just take a look at solving for the total areas under the curve. We talked about how all of these are in the positive domain above zero. Remember that triangles need the 1/2 base times height and rectangles don't. But we could sum that up and we have 1,500. And again, take a look at the units here. We didn't talk about them earlier. So the units for momentum is a kilogram times a meter per second. That's going to be equal to the same as a Newton second, right? And again, how did we come up with this unit? Well, this time we're using the slightly different variation of the Newton second law equation. So you can troubleshoot the math and things like that, but a kilogram times a meter per second is actually going to be the exact same thing as a Newton second. So not only do we have two words that describe the same thing, we have two different units that represent the same thing. And so which one's right? Both can be used. I tend to use sort of which one is synonymous with whichever equation that I'm using. Don't worry about that for right now, but just wanted to give you a heads up. Related to that last problem, though, let's kind of take a look. We have a 5,000 gram object. It's got an initial velocity of 2.5 meters per second. A force is applied to the object as shown in the graph. You can see that that force is not constant, right? So how do we figure out what the final velocity will be after 50 seconds? So again, we can't just sort of use a UAM equation, right, to solve this sort of new velocity because the force is not constant. So again, when do we sort of separate and use this problem approach? So we're going to first figure out that impulse. We did this same kind of calculation a minute ago where we figured out the total impulse acting on it. Oh, my bad. Let me back up. Sorry, it's not the same. For 50 seconds. So my bad. So we're just going to use this orange section and this blue section. So from our previous calculation, we figured out the total impulse during those two sections would be 1,200 Newton seconds. Now, that's not the final answer for this problem because our goal is to figure out what the final velocity would be. So again, this is going to be a setup for setting the impulse momentum equation. The net force times the time is equal to an object's mass times its velocity. So both of those equations mean the same thing. We're going to set those equal to one another. So we have one way to solve for the change in momentum using the area under the curve, which is known as the impulse. We're going to kind of use what we talked about earlier, kind of expanding this equation out, mass times velocity, the change in momentum, right? Final minus initial. And again, from the first part, mass times velocity is a way to solve for a momentum of an object. So the final momentum minus the initial momentum, swing things around so we can isolate and get final velocity by itself. And again, the impulse or the change kind of acting on an object, the oomph that it has is here in pink. That's going to be up here in the top. Plus, right, the initial momentum that the object started with divided by the mass gives us the final velocity for here. So we're going to be doing a lot more practice problems and things that relate to momentum and collisions and things, but just kind of wanted to walk through those equations to get us started. And thanks for listening, and we'll talk soon. Thanks.